Okay, so good morning. This is one of my favorite lectures because it's the one that sort of overturns the tables on what you learned in your freshman year and used in your organic years. So organic semesters. I don't know if it was years. And so we're going to compare local bond theory and molecular orbital theory, since we're in the section where we learn about molecular orbitals and how molecules are actually bonded together. So let's review a little bit about local bond or valence bond theory. So this is the theory that you grew up with, if you want to say it that way, about Lewis-Dot formulas, and two electrons make a bond. So each bond consists of two electrons, and those two electrons are between the bonded atoms, which makes sense. The bonded atoms are positive, they have positive nuclei. Even though they have mostly, like all of their core electrons, those don't participate in bonding. If you take away those valence electrons, even if you take away one of them, that's a positive cation now, and it's going to really strongly repel other cations. And so we're taking these valence electrons and sharing those valence electrons. And so we're putting those two, for local bond theory, putting those two directly between the bonded atoms. So that's the local part of local bond theory. The valence piece of valence bond theory is that you're using the valence electrons. That's actually the same in terms of MO theory, but valence bond theory and local bond theory are the same. So those should be coupled in your mind. The 8-electron noble gas configuration is unusually stable. We saw that from the first ionization energy. And so we acknowledge that there's something nice about having 8 electrons surrounding the atom, whether it's the wave functions, that electron correlation term, we don't know, but something makes that electron configuration shield the nucleus really well, and it sort of protects that atom from being reactive. So that's why the noble gases don't really form that many compounds. You can get the larger ones like xenon to form compounds with fluorine, but for the most part, the noble gases don't react. And so therefore, stable molecules will have many atoms in their structure that have 8 electrons nearby. And so that's local bond theory. This is also called the octet rule. You know about that. It is strongly adhered to by carbon, nitrogen, oxygen, and fluorine. So most of the time when we were making, Lewis-Dot structures and coming up with the Vesper shapes and so on, for you guys when you were freshmen, we were sticking to those atoms because those had octet rules. And then when we would go to larger atoms like phosphorus and so on, we would sort of teach those as exceptions. But if you look at the periodic table, it's like 92 exceptions and 4 that follow the rule. So that's kind of a problem. So we'll find out later that this idea where you have a rule that applies to 4 things out of 100 or more is what we call ad hoc. It's like for this situation. So Latin ad hoc just means for this. So for carbon, nitrogen, oxygen, and fluorine, we strongly adhere to the octet rule. What that means is we make double bonds. So we make double bonds to oxygen or double bonds to the nitrogen and so on. Elements in periods greater than 2. So remember that the hydrogen helium is row 1. So row 2 goes through carbon, nitrogen, oxygen, fluorine, neon. And so then from row 3 down, you can have 5 bonds with phosphorus or what have you. You can have, the bromine molecule, let's see, BrCl3. It has 3 bonds and 2 lone pairs, so it has 5 electron domains. And sulfur hexafluoride, sulfur has 6 bonds. You can't make oxygen hexafluoride. It's just too small. So that's what we call, and I've heard scientists in the past, and when I was taught it, they called it an expanded octet, but sulfur hexafluoride, that's not an octet. That's 6 bonds, right? So that doesn't make sense. So that's a stupid term in my opinion. So you can say it if you want, but I'll sneer at you if you talk about an expanded octet. Okay, just say it has more than 4 bonds. Okay, so that's local bond theory. And we get to those using the Lewis-Dot structure. So let's talk about the Lewis-Dot structures. This, again, is some review, just to kind of go back over the basis of this. So we sum the valence electrons for the whole molecule, and we'll put this into practice on water and CO2 in a second. We create the single bond network, often around a central atom, and then we subtract 2 electrons for every single bond. Then we place the non-bonded pairs of electrons on the most electronegative atoms first, and then subtract those non-bonded electrons from the total. And then if there's any electrons left over, we put them on the central atom. Okay, and then we form double bonds to give octets for carbon, nitrogen, oxygen, and fluorine. And then optional, we can create double bonds to reduce formal charges, like we do in the sulfate ion. So we can look at that example as well. So let's do some Lewis dot structures just to review. And then at the end, once we have all of those bonds, we use the electron pair repulsion theory. So we have this valence shell of all these bonds, we count up the domains, and we create the different 3D molecular structures. So let's practice with water. This is super simple. We've got 1 valence electron for each hydrogen. So each hydrogen has 1, plus 6 for the oxygen, equals 8 valence electrons. Make the single bonded network. Okay, I'm going to do it the freshman way. We're going to just do this. Okay, and so we've used up 4. So we've used up 4 bonded electrons. We have 4 left over, and we put them on the more electronegative atoms. So electronegativity sort of maxes out at fluorine. We ignore the noble gases. So fluorine has the highest electronegativity, and then going left and going down, the electronegativity drops. So oxygen wants those electrons more than the hydrogens, and so we put them on the oxygens. So we subtract those from the whole, and we end up with 0 electrons left over. Then we add in that valence shell electron pair repulsion theory. So we look at the electron pairs. So we have 1 here, 1 there, and then the 2 bonds. And we call those electron domains. And so there are 4. So that means it's a tetrahedral electronic structure. Okay, I want to make sure you understand that, because this is not a tetrahedral molecule. It's just the electron cloud around the oxygen is in a tetrahedral setup, but we only have 2 atoms that are not oxygen, and so it's a bent molecular structure. So we have 2 types of structures. And so we would draw that oxygen here. We would have like a lone pair coming out the front, a lone pair in the back, and then the 2 hydrogens on the other 2 points of the tetrahedron. So that's a bent molecular structure, tetrahedral electronic structure around the oxygen. So I'm going to point that electronic structure at the oxygen, and then the bent molecular structure is going to be the molecule. So the molecular structure talks about the whole molecule. The electronic structure talks about the local structure around a particular atom. And so we could talk about in a more complicated atom, say we've got a carboxylic acid. So this oxygen has a tetrahedral electronic structure, but this carbon here has a trigonal planar electronic structure. So notice how the electronic structure is based on individual atoms. And so you wouldn't say that this molecule is tetrahedron or this molecule is trigonal planar. You talk about specific atoms having an electronic structure that's trigonal planar or tetrahedral. And it's the molecular structure. So this molecular structure is just irregular. There's no name for it. Okay. And so for water, we have a name for it. It's just a bent linear molecule. All right, let's do the same for CO2. So we have 6 valence electrons plus 2 times 6 for the oxygens. So that's 18. Single bonds first. 18 minus 4 is 16. Something's not right. Carbon's 4. Thank you. I was like, this isn't right. I was doing ozone, I guess. Okay. I was like, I should get 12. All right, so that's 16 minus 4 is 12. And so then we put the electrons on the more electronegative oxygens. Okay, 2 times 6, we got rid of 12, so we have 0 left over. And then we look at that molecule and then we say, we have carbon, nitrogen, and oxygen. We didn't check down here, but oxygen had an octet. It had 2, 4, 6, 8, so 8 electrons around it. And we look at this one and the carbon is short, okay? So that's when we make double bonds. So in order to fulfill the octet, we make double bonds. So that electron goes in there. So we can share. Now we could make this crazy. We could make like a triple bond to this oxygen and a single bond, but the oxygens are identical, and so they're not going to want to unequally share electrons with the carbon. So we take 2 electrons from each one. Now carbon has an octet, oxygen has an octet, everybody's happy. And then that is a linear electronic structure and a linear molecular structure. I said we would do the SO4, the sulfate ion. You want to do that one? Yes? Okay, I see a few nods. All right, so let's do SO4. And this is a little review for your final, right? So don't complain. Okay, so we have 6 electrons here for the sulfur, 4 times 6 for the oxygen. And then this one always gets people plus 2 for the 2 minus, because it's an anion. Okay, so add all of those up. We got 5 times 6 is 30 plus 2, so 32. So let's make the single bond network. Put a bracket on there and call it 2 minus. Okay, so we've used up 2, 4, 6, 8, so minus 8. So we have 24 electrons, so 8 bonding electrons, and then we have 24 left over. And that works out because we need 6 on each oxygen to fill out the octet, and 6 times 4 is 24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So just like a good accountant, everything balances out. So we're technically done with this structure. All right, we can calculate the formal charges on these, and let's see. So everything has an octet. The sulfur has 8. The oxygens have 8. So let's calculate the formal charges. And so for formal charges, so Fc, formal charge, is equal to the valence electrons minus a new term I'll tell you. I call it the claimed electrons. So this formal charge, okay, this is valence electrons. And then this C is claimed. Okay, so let's figure out what this means. So whenever we say we're going to claim the electrons, we split every bond equally. So let's look at this oxygen here. If we split that bond equally and draw a circle around it. Okay, so this oxygen comes in with 6 valence electrons, but how many can it claim? If you look at everything in that circle, it's claiming 7. because it's splitting that bond in half. So that's minus 7 claimed electrons. So it's a minus 1 formal charge. So that type of oxygen has a formal charge of minus 1. Everybody got that? And all 4 of those oxygens are the same type. They're all minus 1. So that's quite a large distribution of charge in that molecule. Let's do the formal charge on the sulfur. So it comes in with 6 valence electrons, and it can only claim 4. So if we draw a circle around it and break all of those bonds evenly, it only gets 1 electron for each bond. Okay, so minus 4 claimed electrons. So it's a plus 2 formal charge on the sulfur. If you add all those formal charges up, they equal the charge on the ion. So we did something right. So that's a good way to check your work. But if you look at those formal charges, you know why we call them formal? It's not like they've got like a fancy suit on or an evening gown. It's because they're formalism. They're not real. So that's when we say formalism, that means it's just for note-taking purposes or for theoretical purposes. It's a formality. Let's calculate what the formal charges would be based on these Lewis dot structures and their particular types of atoms, like an oxygen with a single bond and the rest of the lone pairs. Okay, but if they were real, what would happen? Like if you had that positive 2 charge in the middle and all those negative 1s on the outside, then we would naturally share more electrons, right? And so we would form double bonds to reduce those formal charges. So we can't do that if this middle atom was an oxygen, right, on the second row. But for sulfur being on the third row, we can do that. So sulfur can bond to more than 4 things. It can have more than 8 electrons around it. So that's why we end up with this structure for sulfate. We end up with, now, notice we have a choice. We need to make 2 double bonds to get rid of those 2 positive charges, and we have 4 bonds to work with. So we have choices. We could pick the north and south, the east and west, or any 2. And so there's lots of combinations. Let's just pick these 2. And so if I make those 2 double bonds and these 2 single bonds, still have my bracket of 2 minus. And now that sulfur can claim 2 more electrons. And so it comes in with 6, it can claim 6, so it has a 0 formal charge. These oxygens have 0 formal charge because they come in with 6 and they can claim 6. If I break that bond and count up the lone pairs, I have 6 electrons. So that's a 0 formal charge. So that's why we have oxygens that want to bond to 2 things, because that's the lowest formal charge in local bond theory. And then these 2 types of oxygens are still minus 1. That adds up to the total charge of minus 2. And that also shows how you could nestle a proton up to this molecule here and one down here, because this is a minus 1, this is a minus 1. And so you see that structure of H2SO4 or sodium Na2SO4. You can put 2 cations with the sulfate anion and you have a happy compound. So that's minimizing the formal charges. And then we would take the 4 electron domains and we would make that into a tetrahedral molecule or ion. Okay, so this is just some review on Lewis dot structures and Vesper shapes. And what we see in symmetry, which we saw throughout the whole course, like this is the infrared spectrum. We see the water vibrations, we see the CO2 vibrations. If we zoom in on those, we see the P&R branches very nicely defined for CO2, and the PQ&R branches nicely defined for CO2's bending motion. And we see that the structure in the infrared matches the local bond theory. So that's great, because local bond theory predicted water to be bent and CO2 to be straight. And it works as a good initial guess for explaining spectra. That's why we've been using it up to this point. So you make the Vesper-shaped molecule, then you can go to the point group flow chart, come up with the point group, use that as the character table. None of that would work if our Vesper shapes weren't accurate. okay, as an initial guess. Now, are they accurate to the exact angles? Like we would say water has a 109.5 degree angle because of the tetrahedral electronic structure? No, but that's not enough to break the symmetry. So it's still C2V, even though that angle isn't a perfect tetrahedral angle. So these tell us that the asymmetric nonlinear rotational signature for water tells us that it's bent. Okay, so local bond theory is supported by rotational and vibrational spectroscopic data. So that's great. So let's get into the electronic structure. So we have the predictions by local bond theory of a certain kind of electronic structure. Can we probe that? So early on, like in the very first of the course, we talked about some experiments that couldn't be explained by quantum mechanics, and one of those was photoelectric effect. You hit the surface with X-rays or UV rays, and electrons come streaming off. Now, they started doing that with metals, and because metals, they're easily ionized. If you look especially like sodium and those, I mean, they don't hold on to those electrons very well at all. And so you hit them with UV light and electrons just come streaming off in a vacuum. Well, you can send those through an energy analyzer. So these electrons are coming out. It's a negatively charged. So every electron has a -1 charge. So the charge is the same. And so you can charge this plate with a positive charge. You can charge this plate back here with a negative charge, and you can steer those electrons. And so they come out with differing velocities. Let's see. I'll just say meters per second. Okay. And this one, this electron is coming out with a tiny little velocity. And this electron is coming out with a huge velocity. And so if we send these through this little slit, just so that we have a nice little entrance where we've got a nice, clean, collimated beam of electrons, and then we adjust this voltage, we could steer those electrons at a particular velocity into this little pinhole and onto our detector. Now, the really fast electrons will come in, and they'll be going too fast to make that turn, and they'll hit the wall. And electrons that aren't moving very fast at all will come in and immediately get steered because they're not moving very fast, and they come in the slit, and then they get steered right into the positive charge. So only a particular velocity makes it through. So this is like a velocity filter. So we hit the electrons with a constant energy, and they come out with different kinetic energy. So what made the difference? So this is, let's just say metal and metal cation. Let's put a plus on there. And we hit it with, let me think about how I want to portray this. Yeah, okay. So this is the H nu, the incoming light. And this is the ionization energy, and what's left over from that ionization energy is the kinetic energy of the electron. And so if that electron came out of an orbital that's close to the surface, it'll have a high kinetic energy, close to the, like I would say the highest energy orbital, then it will have a high kinetic energy. If that electron was what I would call deeper in, closer to the nuclei, then it would start from here, okay, and it would use up more energy getting to the ion and have less kinetic energy because that incoming photon hit down there. So we're just sort of comparing the photon arrow to the arrow it takes to get to the ion, and then the leftover arrow, which would be the kinetic energy of the electron. And so let's think about water. If we were in the local bond situation, we would have different types of electrons. We would have electrons that are between a hydrogen and an oxygen, and we would have electrons that are lone pairs. And so 2 types of electrons. Does everybody see that? We have 2 bonds, but they're identical. And so the OH electrons will be a certain depth or closeness to the nuclei. And then the lone pairs would be a different depth or closeness to the nuclei. And so we would see 2 peaks, lone pairs and bonding electrons. And that's what the data would look like when we scan through these energies. This binding energy is proportional to that kinetic energy, or inversely proportional to the kinetic energy, and then we count the number of electrons that hit our detector. So we shine this light, we scan our energy analyzer, and we see, at this energy we're getting electrons from the lone pairs, at this energy we're getting electrons from the bonding regions. They have a little different widths because the electrons in the bonding regions have a certain cross-section, like it's sort of their spatial extent, and it may be easier or harder to hit them than it would be the lone pairs. So the more spread out or diffuse the electrons are, then the smaller the peak, because they're hard to hit, if you would think of it that way. So let's take a Kahoot. Okay, taking a little while to come up. And so this is just a quiz on determining how many peaks would be suggested by local bond theory. And let's do classic mode. Okay, just a second while I switch this over. Let's see. There we go. So there's your gain pin, 9240272. Does the QR code work from that distance? Nice. They've added little avatars. I don't remember seeing the football helmets in the Vikings. Do you get to pick those? Let's see, we've got 5, 10, 15, 20, 22 people. Oops. Yeah, this makes it more interesting. I like it. Okay. Is anyone still trying to get in? Don't be bashful. Okay. And one more. Anyone left? Okay, I'm going to start. I think you can still join even if we start. Okay, so let's look. So local bond theory, UV-PS predictions. You can close that door if you want, if it's distracting. So how many valence band UV-PS, so UV photoelectron spectra peaks, does local bond theory predict? So this is ethene, and here's all the little bonds in ethene. And so you just count them up. So you've got carbons in the middle here that aren't shown. So carbons here. Let's see how you do. All right, ran out of time. Let's look at the media here. So every different type of bond is a different type of electron. So you have the CH bonds. So every one of the CH bonds really just counts as one type of electron. So that would be one peak. You have the carbon-carbon single bond, so that would be a second type of peak. And then you've got the pi bond, which even though it's above and below the bond is still a separate type of bond, and so that would be a third type of peak, a third type of electron. Okay, let's look at the next one. What are the 3 valence band UV peaks predicted by local bond theory? So looking at these different kinds of bonds, what would we call them? Some of these have some obvious problems. Yeah. Okay, very good, very good. So we're looking at the sigma bond between the CH, so that's this bond here, and in a double bond, one of those is the sigma bond, and one of those is a pi bond. So we have the sigma CH, the sigma CC, and the pi CC. Okay. Oh, propeller head dropped. Okay. How many valence band UVPS peaks would the LB theory predict for CO2? Don't get trapped by the simplicity of that drawing. Okay. This has a lot going on in this molecule, even though it's so simple. Okay, so we've got the oxygens. I think the next one is what are the types of bonds. So let's go to the next one and then we'll explain it. All right, the little space bears moving up here. Oh, so I didn't explain it. I should have explained it. Yeah. So we'll go back to that one. And we just did this one in, if oxygen's sp3. Okay, so that's okay. That's the normal oxygen that we talk about, the tetrahedral oxygen. Okay, very good. So that oxygen, sp3, that means it has 4 identical sp hybrids. 2 of those are the OH bonds, and then 2 of those are the non-bonded ones. What if we made that oxygen sp2? That'd be kind of strange. But what would we have? So I can't draw on the screen, or I would, but if oxygen was sp2, we would have 2 electrons in one of those sp2 hybrids and then 1 in a non-used p orbital. It would still be a bent molecule. And so that would, very good, that would just mean that those lone pairs weren't the same. One was in an sp hybrid, one was in a p orbital, unused p orbital. So I think you've got the idea. It's the different types of electrons. I put this Kahoot in because in the past, and there's one question I think on the homework about, here's a molecule, how many UVPS peaks would be predicted, and people would always ask me, I don't understand how to do that part. So I put the Kahoot in just for you to practice here in class. Are there any questions on these? Let's see how everybody did. All right. I'm going for Space Bear. Oh, that is 3rd place. Okay. Come on. Yay! All right, I like Space Bear. That's nice. I don't know who that is, but Space Bear is cool. Okay, very good. So let's go back. So now water, this is a lot more complicated than local bond theory, isn't it? This is the electronic structure of water. So for valence shell electron pair repulsion theory, We just had to count up the electron domains. We had 4 electron domains, tetrahedral structure, electronic structure, put the atoms on, call it bent, and we're done. This is molecular orbital theory. So what a mess. Isn't that way more complicated? And this is simple molecule. This is water. So it's if we didn't have to go this direction, why would we, right? If local bond theory was good enough, then we wouldn't even worry about this. But let's look at this. We've had to put together the atomic orbitals in oxygen. So we have the 2s orbital, the 2p, x, y, and z. And we had to mix those together with combinations of the 1s orbitals on the hydrogens. And those 1s orbitals could be in phase or out of phase. And those are different symmetries in the C2V character table. And if you look at the dashed lines, you see that there's something to do with the symmetries of A1 mixed with other symmetries of A1. And this one's A1. And so we have 3 different types of groups that mix together and make 3 different orbitals in the middle and so on. And this is what we're going to learn about in molecular orbital theory. But I wanted to put this talk together for you guys today to show you why we need to go to MO theory, because the local bond theory is not supported by the data. So if we take water and we put it into, actually take water, not our theoretical local bond theory water, this is what the UV photoelectron spectrum looks like. We predicted 2 peaks with local bond theory, and we got 4 plus 1. So we got 5 peaks. And that's kind of a mess, because we can't explain that with local bond theory. Why do we have 5 peaks instead of just 2? And these in the paper were labeled with the symmetry species of the particular pieces of the molecular orbital diagram. So the spectrum matches MO theory. And there's a little different order than what Gaussian predicted, but still it matches the MO theory. So let's take that spectrum and put it on its side next to the bonding molecules. So from the literature, this is that spectrum, that X-ray photoelectron spectrum, or the UV photoelectron spectrum, because we're in the valence region. So whenever I say valence band, so this is a UV PS or valence band PS. And remember what PS stands for, photoelectron spectroscopy. Okay. So that's the same thing. Valence band and UV photoelectron spectroscopy and valence band photoelectron spectroscopy are the same. If you do X-ray photoelectron spectroscopy, then you get all the way down to the core electrons. And so you get the 1s electrons and the 2s and 2p's and so on. So you get and the valence band's all crammed at the top. So you can really do X-ray or UV. And X-ray gets the core electrons, and UV photoelectron spectra gets the bonding area. So let's look at these peaks. So the X-ray, when it gets the 1s on the oxygen, which is at a deeper binding energy, and then here we have these. So notice that the highest kinetic energy is up here, and the lowest kinetic energy is down here. Because think about it, this electron pair is really close to the ion. And so if I hit that with a UV photon, I give it this much energy. But this much energy was taken up to get to the ion. So this is H2O plus. So it took that much energy to ionize H2O plus, and then the remaining energy is the kinetic energy of the electron. So everybody follow what's going on here energetically. And so this top peak is the highest occupied molecular orbital. And then this bottom one is the deepest bonding orbital. And then these other 2 are swapped. They're just different order than Gaussian. So Gaussian did pretty good. It got 4 of them, but it just got the middle 2 in a little different order. So does everybody kind of get it? You see what's going on? This is a great tool, this UV photoelectron spectroscopy, because it tells me the relative energies of my electron molecular orbitals. It also validates molecular orbital theory. And so this is kind of troubling because we have a really good theory like local bond theory, and we've got a really good theory like molecular orbital theory. So how do we evaluate two theories? And this is a piece that was never taught in any of my chemistry courses. I didn't get it till just recently, maybe in the last 5 or 6 years, as I started sort of toying around and reading other things like philosophy and so on, and some history books. And I started looking at the historicity, the study of how history is done. And they talked about how to evaluate theories. And I thought, my goodness, that would be so good to teach scientists. And how do you evaluate theories? What are the criteria to say this theory is better than that one? And so here are your criteria. There's explanatory power. So how well does the theory match the data in the original and subsequent data that it attempts to explain? So if you have a data set and you plot say a line through it, how tight does that fit? How does it fit the data that you use to come up with the theory? And then there's explanatory scope. Well, you can use like R values and everything and mean deviations to evaluate the explanatory power. Explanatory scope is how large the data set is. You could do a 2-point calibration. That wouldn't be a very good one because that's going to be by definition a perfect line. You have an R squared of 1, so it sounds great, but 5 points would be better, 5-point calibration, because that has a bigger scope. And then is the data set diverse, meaning is it explaining IR and Raman and rotational spectra and so on. And then ad hocness, that you want as little ad hocness as possible. So those are like patches or fixes to your theory. So if you have a theory, and then you have to fix it, then that's a problem. And the more fixes and patches you have to your theory, that degrades your theory. There's something you're missing if you have all of these extra ad hoc additions. And so does the theory have lots of exceptions or special cases? If so, that's not good. Okay. So let's apply this criteria to local bond theory and to MO theory. So local bond theory, the explanatory power is big. I mean, we can model molecular structures. You could build DNA with local bond theory. In fact, model kits are made based upon local bond theory. You have the little sticks, you have the little paddles for the non-bonded electrons. You can build, you've seen maybe model kits where they built DNA. It's incredibly big. There's some strained, in those rings, there's some strained angles, okay? But you can force it to go together so it's not so strained that it'll break the kit. Try making cyclopropane, you'll break your kit. Because those are 60-degree angles, and you're going to try to take 109-degree angle sticks and bend it down to make a 60-degree angle. You're going to break the sticks, okay? Explanatory scope is big, but it has a big hole in it. So it matches rotational spectra, it matches vibrational spectra, but it does not match the electronic spectra. That's what we just showed with the UV-PS. So local bond theory predicted 2 peaks, but the UV-PS had 4 peaks. So that's a failure. We only showed water, but you could show lots of molecules. It fails for all of them. And then ad hocness, big is bad. Well, local bond theory's octet rule and expanded octets are very similar to these ad hoc patches. Okay, so we can perhaps get rid of those. So these are arguments against local bond theory or things that weaken local bond theory. Now let's apply it to molecular orbital theory. It accurately predicts molecular structures. Okay, and it matches rotational, vibrational, and electronic spectra. So that's great. So the data is more diverse. So it has a bigger scope. It probably has the same power as local bond theory, but a bigger scope. It can do electronic spectra too. And then there's really no special exceptions. You know, you can build just about any molecule and run it through an electronic structure package and create the vibrational, rotational, electronic spectra for all of them. So what do we do with this information? Right? We have an easy theory that has some holes in it. Okay. And then we have a not so easy theory that covers everything. And so what would you prefer to do? Like if you were given the tool and I say, okay, tell me the structure of water, what would you prefer to do? I guess it kind of depends on the purpose. What are you trying to do with water? So I say, give me the structure of water. If I say, give me your best guess on water, on the structure of water. That word guess is really important. What would you use for a guess of this? Local bond theory, absolutely. What if I say, give me the structure of water with the best bond length you could come up with and the best angle you could come up with? Molecular orbital theory, yeah. And so that's what we do. We've incorporated this into Gaussian. You can do local bond theory with a pencil and paper. But if you need to really get the bond length and the angle, you go to Gaussian. And Gaussian incorporates all of these. And it does the structures, it does the vibration, rotational structures, or spectra, and the electronic spectra using MO theory. So MO theory is incorporated into Gaussian. So when you use a Gaussian calculation, you're using MO theory. When you're pencil and paper, Lewis dot, Vesper shapes, symmetry, you're using local bond theory. So there's no problem in using both theories. Just realize that one is going to accurately predict the electronic spectra, and that would be the Gaussian or molecular orbital theories. Okay, so this is what you do. You sort of see what the strengths and weaknesses are, and then you scope the use of a theory. So we're going to scope local bond theory to structural guesses and symmetries. You see, that's taking into account this scope right here, the explanatory scope. So this theory has a scope that's restricted. And so when you're going to come up with an initial guess, use the local bond theory. And in fact, that's what, it's kind of funny. Gaussian does use both in the builder. So in this little builder here, it's using local bond theory as an initial guess. So in the builder, you're using local bond theory, and then you hand it off to the more complicated computational engine and expand the scope of the theory, and you calculate the more accurate information. So that's all I have to say about the different kinds of theories and how to evaluate them. So hopefully this has been good for you. And it's just, these are just two theories. This is what you do as a scientist for all different kinds of theories. And how you decide on which one is compelling to you is what's called abductive reasoning. So abductive reasoning is the inference to the best explanation. And that's really important in forensics, is this idea you've got two competing theories for what happened on this day and time at this place, and you use your inference to the best explanation, the thing that explains the most facts, that matches them the closest, and has the fewest exceptions. I mean, you could always say an alien showed up, did the crime, and then left. That's very ad hoc. Okay. Is it impossible? You can't say it's impossible, but you can say it's not reasonable. It's not reasonable. So, y'all have a great day.